Hammers, it's Mrs. Facca back. Remember how I told you, and you know I love this analogy, instead of a recipe show where it's chicken 4 ways, we're doing enthalpy 4 ways. So today is, what is it, chicken pizza, right? So in the previous videos we did Hess's law, right? We did delta H naught F, enthalpy of formation. This video we're covering bond energy. So I'm going to write that down so everybody remembers which method we're using. And after I'm done this, we'll have to tag in Miss Shearhart and she'll do like a chicken pasta. That'll be calorimetry. So of the 3 methods we've discussed so far, bond energy is the least accurate. It's an approximation, but it's helpful because sometimes if you're not in the lab or don't have access to a lab, you can use bond energies because all you need is a textbook with a bond energy table. So that's one of the advantages. The disadvantage is that it's the least accurate of these 3 methods. So again, we're still calculating enthalpy, but this time our equation is going to be the enthalpy of the sum of the energy of the bonds that are broken in the chemical reaction. So this would be our reactants. And from that, we subtract the sum of the energy from the bonds formed. This would be the products. And I don't think mathematically any of these methods are particularly difficult, but I would say that of all the methods, this is the one students tend to muck up with just little silly mistakes. So just be careful. And if I have oversimplified it, don't take offense. It's just I want to show you the way that you should do it so you don't make silly mistakes that are going to cost you marks. So the question that we have is, use bond energies to determine the delta H, the enthalpy of the reaction for the complete combustion of methane, right? So we know from our previous examples, it's a complete combustion. So we have oxygen as our reactant, and we have our carbon dioxide and water because it is a complete combustion, so we don't have to worry about carbon monoxide or carbon. All right, I'm going to put this as liquid. All right, so this is the equation that we're going to determine the delta H for using the bond energy method. So if you'll allow me, I'm going to rewrite the equation just so I can do it in an organized way. You've probably learned that being organized in chemistry is absolutely imperative. Now, hopefully you realize, oh, Mrs. Facca, you didn't balance the equation. So let's check. No, we've got to still balance the equation. Our hydrogen's not balanced, right? So we've got 4 and we need a 2 here. Okay, so we're balanced. Now, you're going to thank your grade 11 teacher and maybe grade 10 teacher that they taught you Lewis structures, because for the bond energy method, you need to know how to draw the Lewis structures for every reactant and every product. I'm going to tell you the trick that I think is, not really a trick, but a method that I think is important. So, for example, we've got methane, right? So we're going to draw the Lewis structure for methane. Pretty straightforward. And we're going to draw the Lewis structure for oxygen. But we have 2 molecules of oxygen. I want you to draw oxygen twice because that's going to prevent you from making a mistake later on, because you have to remember that we need enough energy to cleave 2 double bonds, not just 1. And now we find the Lewis structure of our products, right? Carbon dioxide, which is non-polar, right? An example of a molecule that has polar bonds within the molecule, but because of the molecular geometry, the bond dipoles cancel, so it's non-polar. So we only have 1 carbon dioxide, so we're good there, and we have 2 water molecules. So again, draw them both. So now we can actually see every single bond that needs to be broken and every single bond that needs to be formed. Great. So now we need to find out how much energy is required to break all of these bonds in our reactants. How do we find that out? Well, you can't calculate that. You have to look on the table, and we have the table in your textbook, and it's in D2L as well. It's the bond energy table on page 307. So that's page 307. Okay, so I look up at the bond energy table and I determine, well, how much energy is required to break a carbon-hydrogen bond? Well, according to the table, it is going to require 413 kilojoules per mole, right? But I'm not just breaking one carbon-hydrogen bond, I'm breaking 4. We always have to multiply it by the stoichiometric coefficients from the balanced chemical equation. Okay, and to that, we're going to add the fact that we need to break an oxygen-oxygen double bond, and that's 495 kilojoules per mole. Right? But there's 2 of them, one for each oxygen. Okay, so that's the energy that's going to require to break all of our bonds. From that, we need to subtract the energy of the bonds formed from our products. So the first one is a carbon-oxygen double bond. So there's 2 bonds that are going to be formed. So we're going to multiply the value for 2. So you're going to have to continue the equation down here. This math isn't hard, but it's big. All right, so we have 2 moles multiplied by, and I have to make mention of this, there is on that table a carbon-oxygen double bond in the table, but at the very bottom of the table there's a little asterisk that has a unique and specific bond energy for the energy of a carbonyl bond, a carbon-oxygen double bond, that belongs to carbon dioxide. So this is an exception, but it's written on the table. So we've got, this should be moles. Ms. Facca has to keep her units, times 2 moles. We've got 2 moles, 799 kilojoules per mole, so that's for each carbon-oxygen double bond, plus the energy from the oxygen-hydrogen bond, and that is 467 kilojoules per mole. But remember, for each water molecule, 2 bonds are being formed, and this is why I think it's important to draw the Lewis structure. A, because you know whether it's a double, single, or triple bond, but also now we count 1, 2, 3, 4. So we have to multiply the energy here by 4 moles. All right, so now we've got our equation set up. It's pretty straightforward math at this point. So the delta H works out to 2,642 for our reactants. That's the energy that's going to be required to break those bonds. And from that, we're going to subtract the energy from when we formed our products, and that's 3,466 kilojoules. And when we add that up, that works out to a final answer of negative 824 kilojoules. Now, does that make sense? Well, for one, it's a combustion reaction. It's exothermic. So if you didn't get a negative sign for your answer in a combustion reaction, then you know something has gone wrong. And combustion reactions generally for methane are going to be around 1,000 kilojoules, so you know that's correct as well. So now we've completed our 3rd way of determining delta H, not F, or sorry, delta H, the enthalpy for a reaction. We've done Hess's law, enthalpy of formation, and now we've done bond energy. Thanks for watching. See you later, chemers.